Hi everyone, we'll start this unit with a look at sequences in series. It's something we've done before with arithmetic series, so just a little something to remember here. A sequence of numbers like this, 2, 5, 8, 11, etc., etc., is an arithmetic sequence because I'm adding the same amount each time. Could be subtraction, etc., etc., etc. And something like this, the nth term, un, would be equal to the first term plus n minus 1, the number of terms that you want, times the difference between the two. So any two consecutive terms, so in this case it'd be 3. And you can clean that up if you want. So you would get something like 3n minus 1 for this one. If you want to add up a whole bunch of terms, then you would use this other formula, if you remember, which is the series. So when you're adding, you call it a series. So Sn, and let's say you wanted the first 10 terms. Etc., etc., etc. 10 terms of this. How would you do that? You'd use that other formula. So it'd be, in this case, if you want the first 10 terms, should put 10 there, equals 10 divided by 2, 2 times the first term, plus 10 minus 1 times the difference, something like that. Or if you wanted to, you can use the second formula. That's if you know the nth term, the 10th term in this case, and we don't. So it would come out to be 9 times 3, so that's equal to 5 times 31, which is, what is that? Someone got a calculator? 155, something like that? Let's go with that. So that's what we had done with arithmetic series. So it's when you're adding the same amount to get to the next term. If we want to look at a different type of series or sequence, it'd be something like this. Whereas you look at these 4 examples here, it's a little bit different. There is a pattern there, but this time you're adding 2 and then you're adding 4. So it's not the same amount that you're adding each time. What you're doing is you're multiplying by the same amount each time. So the next one would be 32, 64, 128, 256, etc., etc. In this case, you can have also negative numbers that you're multiplying by. So how do you get from here to here? You multiply by negative 3, by negative 3, by negative 3. So by negative 3 would be negative 81. And then I think the next one is 243. And then after that, etc., etc. For the next one here, you're missing the first couple of terms, the first 2 terms. Then you got the next term to be negative 6 and then negative 3. So how did I get from here to here? Well, you might say, well, you divided by 2. But it's probably better if you think about it as multiplying by 1/2. So multiplying by 1/2, multiplying by 1/2, etc., etc. So how would I have gotten here? This would have been negative 12 and negative 24, I guess. Just working backwards, and this one would have been negative 3 over 8 and negative 3 over 16. Last one here, how am I getting from one term to the next? I think it's fairly obvious. You're multiplying by 5. So before that, it would have been 1 over 5. I'm just working backwards. I'm dividing by 5 to work backwards. 625. There we go. So something like that. So each term of a geometric sequence can be written in terms of its first term and common ratio. The last one with arithmetic, you had a common difference because you take the difference between any 2 terms, 2 consecutive terms, and you get the multiplier. So this, for example, that's your ratio. So your ratio would be the term divided by the term before that. So for example, in this one, it'd be 16 divided by 8, which is equal to 2. And that always is going to be the same for any two consecutive terms. So what do we call that? We're going to call that common ratio, how about R? That sounds good. And the first term, we're going to call U1, just like we did before. The nth term, we'll call that UN. Okay? So how do we get from one to the other here? Well, if I look at those examples above, maybe I'll kind of look here. You can kind of construct from the first example. So what you do is you start off with your first term, this one, then you multiply by your common ratio, and you get to this without multiplying it out. If you don't multiply it out, you'll see what the pattern is. Times 2 you get this, times 2 you get this, times 2 you get this, etc., etc. So what's the pattern there? For the nth term, what am I doing? Well, I'm taking that first term, and to get to the next one, I'm multiplying it by r. So to get to the second term, I multiply by one of the r's here. To get to the third term, I multiply by 2. And then to get to the fourth term, 3. So I'm multiplying it by r raised to the power of n minus 1. So that's what your equation would be, and it's given to you in your formula booklet. Nice. Okay? So, a couple of questions for you. Can you always write a geometric sequence in terms of its first term and common ratio? Answer? Yes. If you can't, it's not a geometric sequence. Here, good enough. Next, what's the formula for the nth term of a geometric sequence? Well, I just did that one, right? That's un equals u1 r to the n minus 1. That's what we're talking about. And last question, how can you tell if a sequence is geometric? You have to see that the pattern is always multiplying by the same ratio to get to the next term. So if you have something like this, I don't know, 3, -9, 27, is that a geometric sequence? Well, it is. It's hard to tell if there's another way of writing it, but if I give you another one, you start seeing that it's like, yeah, I'm fairly confident that you're multiplying by 3 each time. So that's what a geometric sequence is. Very, very handy. Okay? So an example here. The first 3 terms of a geometric sequence, 3, 6, 12, write down the common ratio. Well, what am I multiplying by each time to get to the next term? The common ratio is 2. I could just do that in my head. If you want it to show work, it's 6 divided by 3, or 12 divided by 6. That's how I got to it. Don't have to show that work. That's pretty evident. B, calculate the value of the 15th term. So you start off by writing down the formula. And then you want the 15th term. So you take the first term and multiply it by r, which is, in this case, 2, raised to the power of 15 minus 1. Now at this point, I realize I do not have a calculator. So I'm just going to leave that to you to finish the job. Okay? It'll be some big number. Do be careful here, a couple of things. One is be careful. Don't multiply these 3 times 2 first. Don't do that. Order of operation. You got to do the exponents first. Okay? And the other thing to watch out for here, I would think, is to don't get into the habit, yes, I'm talking to you, Otto, of just doing it in your head or trying to do it in your head. You're going to make some mistakes along the way here. So watch out. What else? That's it for now. Another example. Application problem, since it is what this course is about. So a plant is 0.5 meters long. Every week it grows by 20%. Now, little thing here about these questions is if you see a percentage increase like this, regular percentage increases, it is in fact geometric. These are multipliers. So if ever you see a percentage increase, so guess what a nice application will be? It'll be something like interest rates, and we'll get into that in a couple of lessons. Okay, so 2a, find the value of the common ratio. Well, okay, with percentages, you might say, well, you multiply by 20% or something like that, but that'll actually reduce it. So what you need is you have to add it to the original 100%. So the common ratio for percentages, don't forget to add the 100%. So in this case, it'll be 100% plus 20%. You don't have to write that down, but it'll be 120%. But more commonly, the way we write it is 1.2, because a percentage is divided by 100. Okay, so that's how you get that. With B, calculate how long the plant is after 12 weeks. It will be, you want to know, U12. So it'll be original amount and times R, which is 1.2, and then after 12 weeks. Again, no calculator, but you can do that. Okay? And C, comment on the predicted length of the marrow after 1 year. Well, the thing with 1 year, this is how much it grows every week. So you're asking for 52 weeks. Now, you got to be careful here. With exponential growth, things grow very quickly. Okay? If you look at the graph, it looks like this. Okay? So what happens is if you get a few points of data on a real application, it may work very nicely like this, like you saw in the last video. But after a certain amount of time, it doesn't make any more sense. Things can't grow exponentially forever in nature. There are limits on it. It could be a food restriction, it could be a size restriction, etc., etc. So in this case, would a plant grow by the same amount for 52 weeks of the year? Generally, no. And you'll probably get a number here that's way too big. It'd be interesting just to work this out to see if it makes any sense. Okay? What else we got? Flu epidemic. This sounds familiar. In Cozy Town. Who makes these names anyway? That's terrible. On the first day, 2 people have the flu. Second day, 10 people have the flu. So if you kind of write this out, so U1 would be equal to 2, U2 would be equal to 10, and U3 would be equal to 50. Right? So if I'm going from one to the other, I'm multiplying by 5. So R is equal to 5. Okay? So for A, show that it's geometric. The way you show these things is you have to show that this is a constant multiplier. So I suppose what I wrote above my A here is sufficient, but if you want to make it look slick and fancy, you could say something like this, that you divide all those consecutive terms and you always get the same answer, 5. Then you put a nice sentence there, which I'm not doing. And hence, assuming the conjecture is true, calculate how many people have the flu after 1 week, which is 7 days. So they're basically looking for U7. So that's U1 times your ratio, raised to the power of 7 minus 1. There you go. Work out the number. Considering what's going on right now with the coronavirus, these are the kind of numbers. And if you look at that last video, or if you're looking at the news, this R number, this multiplier number is very, very, very important to the medical community and to everyone around. if r is less than 1, then you have a shrinking rate. So if you're thinking of transmission of disease, it means that if you have it, on average, if a person has it, if your ratio is less than 1, it means you'll spread it to, like, let's say r is equal to 0.8 for an example, 0.8 of a person. So if you want to kind of think in large numbers, if you have 100 people with the disease, they'll pass it on to 80, which is actually means that it's decreasing, because those people that are originally infected will actually have, will be kind of recovering, hopefully, from the disease, and there'll be fewer and fewer people with active cases. So this is the whole goal of trying to kind of control the propagation of a flu, or the coronavirus in this case, if you can get that number down to 1. How do you do that? Isolation is kind of the what people seem to have adopted worldwide here for this one, because they don't have like a shot or something like that. So they just stay away from each other and try to control that. So if right now their guess is that if you don't control things with the coronavirus, you're looking at a transmission rate of over 2. So on the news you'll hear numbers that r is between 2 and 4, which means that for 100 people that have the disease, between 200 and 400 will pick it up from those original 100 people. So these are massive, massive numbers, and it grows very, very fast. So that's what they're working on. And some countries seem to have gotten that R number below 1. The ones to think of is China and Korea. Anyway, let's move on here. Here's another one. Second term of a geometric sequence is negative 32. Let's write that down. And the fourth term is equal to negative 2. Seems to be decreasing. Given that all the terms are negative, find the common ratio and the first term. Okay, for this one, one thing to notice on a question is it says here geometric. I know that sounds obvious, but it's telling you it's geometric. So you know you're multiplying to get from one to the next. Some of you will probably try to figure out, well, I'm multiplying it by something to get here, and then I'll multiply it again by the same number to get here. And you'll just kind of do that in your head. That's nice, and you can do that. Some people have more difficulty with that. So if I kind of expand on this, make a little more room. So they're saying, okay, in your head, you just kind of like guess at what the number is. Anybody can figure that out? Take a look at this. It's going down, so you're going to be multiplying by a fraction. And then, right, so I believe it's 1/4. Hope that's right. Because 32 divided by 4 is 8. Negative 8 in this case, because it's negative 32. And negative 8 divided by 4 is negative 2. So that'd be my R value. Not obvious for everyone to do that. So how do you do it otherwise? What you can do is this. The second term, if you don't know R or the first term, what you can do is just write down what you know, and then use your formula. So U2, for example, is equal to, well, just remember, UN is equal to U1. Let me back up a little bit here. I approached that the wrong way. The formula is UN equals U1, R to the n minus 1. Now let's write down. We have 2 bits of information, this one and this one. So if I take the first one, I know that UN is negative 32 when n is 2. I don't know what this is, and I don't know what R is, but I know n is 1. So 2 minus 1 is 1. And the second bit of information is that U4 is equal to negative 2 when n is 4, so that's 4 minus 1, so that's 3. And what it can do is you have 2 equations here with 2 unknowns. Now with these geometric series, what you can do is divide. So in this case, I can say the second equation divided by the first equation. So what does that give you? Well, negative 2 divided by negative 32 is, yes, 1 over 16. And then on the other side, u1, so again, what I'm doing is, if I stack it up the way I wanted it to, like that, and I'm dividing these two. So this is a little aside here. So negative 2 divided by negative 32 is negative 1 over 16, and u1r cubed divided by u1r1, well, u1, they cancel out, and r3 divided by r1 is equal to r2, right? Because you subtract the exponents when you divide. So you get this. So then you go and you solve for r. Now remember, when you take a square root, you get a plus minus. So the actual answer would be plus minus 1/4. And that's the thing, but they do mention to you here, they right here, that all the terms are negative, so therefore, for that to work, r would actually have to be the positive one only. I could have had the negative in there, but they actually tell me don't use that one. You may not have noticed that, so watch out. Won't really happen in SL, but HL, they like to trip you up sometimes. So a little something there. So I got the common ratio, and let's not forget to answer the whole question. They also asked for the first term. So what's that going to be? Well, I now have un equals u1 r to the n minus 1. I now know what r is, so I need to find u1. So I can use one of my 2 bits of information. Let's take u2. I know that un is equal to negative 32 when n is equal to 2. And the r value is 1/4. I know that now. So something like that. So negative 32 equals u1, and then it's 1/4 raised to the power of 1. Multiply both sides by 4, or if you want, divide both sides by 1/4, and you get negative 128 equals u1. So I get that answer, and I get this one. So I've answered my question. Okay, I know some of you could have also done that one in your head, negative 128, because you just say, well, if it's multiplying by 1/4, to back up, I have to multiply by 4. Okay, you can do that. But sometimes it's a little tricky if it's the term is like, you know, the 7th term and the 10th term, because then you got to do a lot of those divisions or multiplications. Whew. One last one. Population 1. Okay, so they give you an initial population in 2016 of 200,000 people. And at the end of 2018, the population was 264,500. Now, I think that's U3. Correct me if I'm wrong. Because this is at the end of 2016, this is the end of 2018. So 2 years have gone by. So if I start at U1, U2 would be 2017. Now, you could say, well, you're just adding the same number each time and it's arithmetic, but again, the question tells you it's geometric. So there's that. So in A, find the population at the end of 2017. Okay. Well, to be able to do that, you can kind of work it out in your head, I guess, but I think I'm going to have to approach it the same way I did last question. So if I look at this, 2 bits of information, and I'm going to divide the 2, just like I did before. So I'm going to do this one quickly. So remember, un equals u1 r to the n minus 1. So u3 is equal to 264,500. And that will be equal to u1, which is 200,000. Oh, I know that one, so it won't be 2 unknowns, at least. 200,000 r to the n minus 1, which will be 3 minus 1. So I can solve that. That one's actually not so bad. Of course, I don't have a calculator. Did I mention that? R squared. So what would I do? Well, I'm not going to have a calculator with me. So again, hope you guys brought your calculators. So R here will be equal to the square root of whatever that is. This does not have to be nice numbers. Now you might say there's a plus minus here, but in this case, the logic dictates that it's going to be the positive one. Because you're not going to fluctuate to a positive and negative number back and forth when you're talking about population. So sometimes you just got to use your common sense. Once I have that, calculation of population at the end of 2020. 2020 means that n is equal to, let's see, 1 was 216. I think that's 5. Am I correct? I think so. And you can put that into your equation because you will know the ratio based on A, and you know the first term, 200,000. And C, comment on whether this increase will continue, give a reason for your answer. I'll leave that to you, but I think the obvious answer is not forever. There will be physical limitations to how much population a city can support. Now, you may argue that and say, no, we can keep building, coming up with new technology, etc., etc. Eventually, you will work. Like, it simply will not be possible. Out of interest, you can kind of work out the problem so that you can say, well, when does it reach at least 1 billion people? How many years will that take? These are questions that can be asked of you also. Anyway, I'm going to stop here, and we'll continue on the next video. See you later.